Hi, welcome to the lecture number 52 of fuzzy sets, logic and systems and applications. In this lecture, we will continue our discussion with Mamdani fuzzy model. So in Mamdani fuzzy model, let us understand the fuzzy reasoning of Mamdani fuzzy model for the following. Mamdani fuzzy model using max-min and max product composition for fuzzy and crisp inputs. We have already discussed the fuzzy input for Mamdani fuzzy model using max-min and max product compositions in our previous lecture. So we have already discussed the Mamdani fuzzy model using max-min and max product compositions for fuzzy input with single rule and single antecedent. When we feed the input as the crisp value, so this means that when we apply x as crisp, means the input means the crisp input we apply. So we see here that the rule, we have a single rule in Mamdani fuzzy model. So, and in this rule we have a single antecedent here, only one antecedent. When we say only one antecedent, it means we have x is a. But when we say multiple antecedent or two antecedent, then here we would have x1 is a1 r and x2 is maybe a2 or something like that. So multiple antecedent scenario would have been like that. But since here we have x is a, it means single input we have in this fuzzy model. So let us now apply the crisp input here like this. So the value of x here is the value of x input, the value of input x is a crisp value which is 6.8. So let us now apply this. So what we do here is we simply take this fuzzy set which is here as the input. So we have a, let us have a fuzzy set like this. Then we find the intersection point. We draw a line at, you see here in between 6 and 8 we have point 6.8. So this line gives us x is equal to 6.8. So this value of the generic variable corresponding to this, we have the membership value 0.34. So 0.34 we get here. Please note that when we have a crisp input, so the point of intersection is going to be only the single value. So here there will not be any conflict, as we have seen in the case of the fuzzy input. So in fuzzy input we can have multiple points of intersection, and then if we would have gotten the multiple points of intersections, we would have taken the maximum of these two. But here we have a single point of intersection. So this is our W, which is the weight. So we have a single W, so even if we take min, that is going to remain the same, or even if we are going to take product, the W is going to remain the same because we have the single value. So with this we'll move forward and we use this value to truncate the output fuzzy set. Output fuzzy set here is B. This is the B fuzzy set. So when we do that, we see that point corresponding to the input x is equal to 6.8, we have this as the W, and we use this W after either min or product. This remains the same 0.34 because we have the single W. So we proceed further and we use this value to truncate the output fuzzy set B. And again, as I mentioned, since we are using max min composition, so whatever we are taking first min and then we take the max here. Whatever we get, we take max. So max would have been applicable when we would have multiple rules applicable, and so the outputs of all these rules would have been aggregated, or uh, output of all these rules would have been taken as the union of all these. So the max is going to give the same value as we have here. So this is the B dash, and this B dash will remain the same even if we take max, same here. So that's how the corresponding to x is equal to 6.8 is giving us the output as B dash, and this is nothing but what? This is the fuzzy value. But this fuzzy value has no meaning unless we understand it, like what is the corresponding crisp value out of it. We have fed the crisp value to the model, but we are getting the fuzzy value. So this fuzzy value has to be defuzzified to be further used. So we'll discuss in the last as to how we convert this fuzzy value into the crisp value by uh, uh, various kinds of defuzzification modules. So here, this fuzzy model, which is basically having the single rule with single antecedent based on the crisp input, that is x is equal to 6.8, is giving us the fuzzy output, the fuzzy value as the output, which is nothing but B dash. Similarly, the max product composition for the same input is going to give us the same output, because the product is also the product of the W here, the weight. We have the single weight here. So the product is also going to remain the same, and with this value, with this weight value, we move further and we truncate and we are going to get the same output. So x is equal to 6.8 is going to give us the same output. This is the fuzzy value as the output. So whether we have here in this case the composition, max product or max min, both are giving the same output, and we know the reason, because in both the cases here, in this case only single rule with single antecedent is applied. So single antecedent will produce only the single weight here, single weight W, and the whether we use the max, whether we use the min or uh, product, this is going to give us the same. So that is why the max product or max min, both the composition are going to give us the same result. Now let us move to this second scenario where we have the single rule with multiple antecedents. So we have a Mamdani model we have a Mamdani model here which has only one rule, but this rule has multiple antecedent, means the premise part has multiple antecedents. So let's see how does it look like. So you can see here we have a rule, this rule here, and in this rule we have the premise part, which is this, and then the consequent part. So this is the premise part, and this is the consequent part. So in premise part we see that we have two antecedents. What are those two antecedents here? First antecedent is x is a, and the second antecedent is, so second antecedent is y is b. So this is the first antecedent, and y is b is 2, the second one, the second antecedent. So these two antecedents are connected by AND. So AND is nothing but a connective. This could be by OR as well. So we have a fuzzy model, Mamdani fuzzy model, which has a single rule but two antecedents under the multiple antecedent case. And here also we have the inputs, but the inputs are two inputs here because we have two antecedents. So x and y both are the inputs to the model. Now this x and y can be either crisp or fuzzy. We'll discuss both the cases. Now coming to the consequent part, in consequent part we have z as the output and c is the fuzzy value. So consequent part is fuzzy. So when we see this rule has the premise part fuzzy because a and b both are fuzzy, and the consequent part is also fuzzy because c is fuzzy. So the rule type here is that the premise part is fuzzy and then the consequent part is also fuzzy. Now coming into the premise part, let us first understand that we have two antecedents. The first antecedent here is x is a, second antecedent is y is b, and both these antecedents are connected by connective AND. Here this AND, in place of AND there could be other connectives like or but. So but in this case we have AND as the connective. So we have in this premise part, which is fuzzy, we have two antecedents, and these two antecedents have basically x, y as the generic variable values as the input. So x, y are the input. So I hope this is very clear now. So with this, the fuzzy Mamdani fuzzy model is available. Now what happens when we apply the inputs x and y to this model? What is the kind of output that it generates? So there can be two scenarios. The first scenario here is, in this case, that x, y can be the fuzzy input as we have seen in the previous case. X and y can be the fuzzy inputs. X and Y can be the crisp inputs, and then here also we can have max min composition and max product composition. So let's now go ahead and see the various cases. So here we see that we have the model available and we have the rule. In this rule we have the antecedent, two antecedents. So here we have the first antecedent. So this is our first antecedent where we have X is A. So here this is the first antecedent. The second antecedent is here. So I can write here the first antecedent. The second antecedent. Then we have the output. This is the output. So this, since this model is known, it means capital A, capital B, capital C, all these three fuzzy sets are known. Now, let us apply the input X, Y. So we call this as the fact here. So let us apply the input X and Y, and let us apply fuzzy inputs. When we say fuzzy inputs, it means we give the fuzzy value, and fuzzy value we all know that fuzzy value means a fuzzy set. So let us give X is equal to A dash, Y is equal to B dash, small x, small y, small z. So now let us do that. So since here X, Y both are fuzzy values, so they are represented by the fuzzy sets. You see here A fuzzy set, A dash fuzzy set, B dash fuzzy set. Both the fuzzy sets are here. Now let us apply. This was the rule which is already known, and this model, Mamdani fuzzy model, when we apply this input, means X is equal to A dash, Y is equal to B dash, let's see what it is going to produce. So again, like in the previous scenario, we superimpose these two fuzzy sets to their corresponding input fuzzy sets. So A dash here is superimposed to A because X is A dash and then Y is B dash. So this also is superimposed to the fuzzy set which is already known. So we see that when we superimpose these two, we see the point of intersection here, and we call this as the W1. So let us represent this by the W1. So this is W1, the intersection point. So this is the first weight. Similarly, here when B and B dash intersects, let's say this is W2. So these two are two different values of weights, and these weights are nothing but the corresponding, you see here the intersection corresponding membership values. So you can easily get the corresponding membership value and you call this as the W1. Here also you get the corresponding membership value and you call this as the weight 2. So these two weights are available. Now if we apply max min composition, so we take min of these two. So min of these two values, min of 0.58, min of 0.58 and 0.36, obviously the min of these two is going to be 0.36. So we'll take 0.36 and we proceed truncation with this value. So 0.36 we use for truncation, and this is what we are getting as the min value, min of the two, W1 and W2. So this is the output of the first rule. I mean, we have only one rule, so the output of this rule. If we would have multiple rules, where we'll see that in coming slides, then we would have taken max of all these. We would have aggregated the outputs of all the rules. So here, since we have only the single rule, so this will become the output corresponding to the inputs x is equal to a dash, y is equal to b dash, connected with a, connected with AND. So you see, this is what is the output that we are getting, the same output here, because the max is here. Since we are using max min composition, max is not really applicable because we have the single value, single rule, the output is single. So the max is giving us the same thing, whatever is here is coming as the output. So this way, in the second scenario, we get the output. So here, in this case, the input is fuzzy. So you see here, the input is fuzzy values, or the fuzzy sets. Now, in the second scenario, what happens when we use the max product composition? So with the same inputs, same set of fuzzy inputs. So everything remains the same, as we have already seen that the intersection point is designated as the W1, and here's W2, the weights, and weights we have already seen that 0.58 and 0.36. So here, since we are using max product composition instead of max min, where we have taken the min of W1, W2, here we are taking the product of W1 and W2, because we are using max product composition. So we'll take the product of W1 and W2 and the product of 0.58 and 0.36. You see, there is W1 and there is W2. When we take the product, we are going to get the final value, that is the product of these W1 and W2. We are getting 0.21. So since we are getting 0.21, we truncate with this membership value with this weight value, which is 0.21. So we see, as compared to the previous case, the fuzzy value is lesser than that of the max min case. So since we have, now we cannot take the max because max is really not applied, we have only single rule. So the same output is transferred over here. So we see that we have the C1, we call this as the C1 as the output. So max product is giving us again the fuzzy output, and this we can defuzzify to get the crisp output. This fuzzy output is in the form of the fuzzy set. So in the second scenario, we have seen that how max product, max min produces the output for fuzzy inputs to two antecedents. Now, next is in the second scenario itself, instead of fuzzy inputs, let us take the crisp inputs. So again, on the same lines, we see that we have the rule here, which is the single rule, but multiple antecedents. So here we have two antecedents instead of under multiple antecedents, we have two antecedents. This is first antecedent, first, and the second. First antecedent, second antecedent. And here we have the output. So when we apply the inputs as crisp values, it's very simple. Instead of fuzzy, where we applied the fuzzy value in form of fuzzy set, so there we could have multiple points of intersection, and we could have avoided this by taking the max within that antecedent. Here, that case will never exist, means the conflict will never exist. Rather than we are going to get always the single value, single intersection value. You see here, for x is equal to for x is equal to 6.5, for here xy, there is a small x, a small y, here also a small x, a small y, small z. So when we take x is equal to 6.5, y is equal to 8.5, we get the point of intersection as W1, point of intersection as W2, and this way we have two points of intersection. Now for max min composition, we have to take min of these two, min of W1, W2. So when we take the min of W1 and W2, we get again the we get 0.36 here, and since we have only one rule, so maximum of the max min composition doesn't apply here, and the truncated value here, the fuzzy value, will become the final output. So this is the final output of the model corresponding to the fuzzy input x is equal to 6.5, y is equal to 8.5. Now what happens when we take the max product composition? Since we already have this W1, the weight, W2, the other weight corresponding to the x is equal to 6.5 and y is equal to 8.5. So when we multiply this, when we take the product of these two weights, we see here, we get W is equal to 0.29. So with this value, that is W is equal to 0.29. So with this value, we truncate the fuzzy set C. So with this value, we get the output. This is the output out of the first rule. This is the fuzzy output. The truncated shaded area is the output, that is fuzzy output basically, fuzzy output. And then again the max is not applied here because we have only one rule, single rule. So we don't have to do anything further, and the same output is the becomes the final output. So the same is the final output, that is the fuzzy output, which is in the form of fuzzy set, the truncated fuzzy set. I can write here the fuzzy output. Now we can use suitable defuzzifier to convert this fuzzy output into the crisp value. So in today's lecture, we have discussed the following: Mamdani fuzzy model using max min and max product compositions for single rule with single antecedent for crisp input. And also we have discussed the Mamdani fuzzy model using max min and max product compositions for single rule with multiple antecedents for fuzzy and crisp inputs. And in the next lecture, we will continue our discussion with remaining part of the Mamdani fuzzy model. Thank you.